Good morning, friends. In this lecture, we are going to see an example problem for design of doubly reinforced beam. Let's get started. Problem statement. Design a simply supported beam for the following data. Clear span 4.77 meters, wall thickness 230 mm, live load 24 kilonewton per meter, M30 grade concrete, Fe 415 grade steel, and nominal cover is 30 mm. The following steps are followed in this design: geometry, load calculation and analysis, check for adequacy, calculation of area of steel, check for shear, check for deflection, and finally the detailing. Let's start the design. Step 1: geometry. So in this step, we are going to determine the effective span and then width as well as effective depth and overall depth of the beam. So initially we need to know the effective span as per the IS code clause 22.2.a. The effective span for a simply supported beam is given by the summation of clear span plus effective depth or center to center distance of the support, whichever is less. Initially we are unaware of the depth of the beam, so let us take the effective span as center to center of the support. So effective span is calculated as 4.77 plus 0.23 upon 2 plus 0.23 upon 2. So the sum is 5 meters. Effective span is 5 meters. Depth of the beam is obtained from span by D ratio as given in clause 23.2.1.a. So span by D ratio equal to 20 for a simply supported beam. But in order to be on the safer side, we are going to reduce the span by D ratio. So let us assume a value something between 12 to 15. So I'm taking 15 in this case. So assuming span by D is 15, the effective depth required is 333 mm. Effective cover is the sum of nominal cover plus stirrup thickness plus main diameter divided by 2. So nominal cover is 30 mm as given in the problem statement. Let us assume 8 mm diameter for stirrup bars and 20 mm diameter for main reinforcement bars. So let's calculate the effective cover. So 30 plus 8 plus 20 upon 2. So D dash, the effective cover is 48 mm. Overall depth is the summation of effective depth and effective cover. So overall depth D equal to 333 plus 48, which is 381 mm. So let us provide a value which is slightly greater than this 381 mm. So I'm considering 400 mm. So let's calculate the revised effective depth. So effective depth equal to overall depth minus effective cover. So we get 352. And since it's a simply supported beam, I'm considering the width of the beam equal to the width of the wall. So width of the beam B equal to 230 mm. Step 2: load calculation and analysis. So in this step we are going to calculate the self weight, then add it to the live load to get the total loads, then apply moment and shear force equations to get the maximum bending moment and shear force. Let's do it. Self weight of the beam is given by cross sectional area into unit weight of concrete. So here we have the cross section as 230 by 400 mm. So 0.23 into 0.4 into 25. So we get 2.3 kilonewton per meter. Live load as given in the problem statement, it's 24 kilonewton per meter. So the total load is 26.3 kilonewton per meter. The maximum bending moment for a simply supported beam with UDL is WL square upon 8. So we are substituting the values. W is 26.3. Effective span is 5 meters. So substituting in the moment equation, we get the maximum moment is 82.19 kilonewton meter. We have to multiply it with partial load safety factor, It is 1.5 for dead load and live load combination. So the ultimate moment mu is given by 1.5 times m, so which is 1.5 into 82.19. So the ultimate moment mu is 123.29 kilonewton meter. Maximum shear force is obtained at the support. So the reaction is the maximum shear force. So V is given by WL upon 2. So 26.3 into 5 upon 2, we get the maximum shear force. V is 65.75 kilonewton. We are applying the partial load safety factor of 1.5 for dead load and live load combination. So we get the ultimate shear force VU equal to 1.5 times 65.75, which is 98.63 kilonewtons. So we have obtained both the ultimate moment as well as ultimate shear force. Step 3, check for adequacy. Now in this step we are going to find out whether the beam is singly reinforced or doubly reinforced. So let's do it. So we are going to deploy the equation from class G 1.1c of the codebook. Mu comma limit is calculated from this equation 0.36 into xu max upon d into 1 minus 0.42 into xu max upon d into bd square fck. And xu max by d limitation is taken from the class 38.1 nodes of IS 456, so which is 0.48 for Fe4 and 5 grade steel. Now substituting the values of FCK, B, effective depth D, and the XU max by D, so we get the mu comma limit, which is 117.95 kilonewton meter. Now in this case we have obtained mu, which is 123.29 kilonewton meter, which is greater than this mu comma limit 117.95 kilonewton meter. So the section is doubly reinforced. So that means like we have to calculate AST1, AST2, and as well as compression steel ASC. Step 4, calculation of steel. Area of steel is calculated in two terms here. So one is AST1, the other is AST2. Now AST1 is calculated by using mu comma limit value, that is 117.95 kilonewton meter, which is substituted in the equation G1.1b. So we will get AST1. Now substituting moment as 117.95 into 10 power 6, and Fy is 415, Fck is 30, width is 230 and depth is 352. So we get a quadratic equation. Resolving it, we get AST1 is 1157 mm square, and AST2 is calculated for the moment which is higher than mu comma L. So mu minus mu comma L is the higher moment. So for that moment, the balance moment, so we are going to calculate AST using the equation mu minus mu comma L equal to 0.87 Fy AST2 into D minus D dash. So substituting the values here, so we are getting AST2 is 49 millimeter square. AST is the total amount of steel to be provided, which is the summation of AST1 and AST2. So 1157 plus 49, we arrive at 1206 mm square. Now let us assume 25 dia bars are to be deployed. So number of 25 dia bars required is area of steel required upon area of 125 mm bar. So 1206 upon 491. So 491 is the area of 25 mm bar. So we get 2.45. So that is 3 numbers. So area of steel provided is 1473 mm square. That is 3 into 491. So we get 1473 mm square. So assuming the other possibility. So assuming 225 mm bars and 120 dia bar. So that is 492 into 2 plus 314. So we get is 1296 mm square. So that means like we are saving steel. considerably. That is like around approximately 180 mm square we are going to save. So let us provide 225 mm bar throughout at the bottom and 120 dia bar which will be curtailed uh, from the face of the support by 0.08 times L effective, that is 400 in this case. So area of steel provided is 2 into 491 plus 314, which is 1296 mm square. So the percentage of steel provided is 100 AS upon BD. So we get is 1.6. Substituting the values, we get percentage of steel provided in tension is 1.6 percentage. Compression steel. So other component is ASC, area of steel in compression. So for this we need to find out this stress in steel corresponding to a strain of E epsilon x equal to 0.0035 xu max minus d dash upon xu max. So we are substituting the values. Xu max is 0.48 times 352 and d dash is 48. So we are assuming the same cover is provided on the top also. So the effective cover is 48 again. So epsilon s, that is strain in steel, is 0.0025. Referring to table A of SP16, we are finding out FSC, so which comes out to 345.26 Newton per mm square. Now substituting this in the equation as per clause G 1.2, page number 96 of the code, mu minus mu comma L equal to FSC AST2 into D minus D dash. So 123.29 minus 117.95 into 10 power 6 equal to 345.26 into AST2 into 352 minus 48. So ASC equal to ASC equal to 51 mm square. Let's calculate area of steel to be provided in minimum as per class 26.5.1.1a. So A is minimum upon BD equal to 0.85 upon Fy. So when we substitute the values of B, D and Fy, we get A is minimum as 166 mm square. So ASC calculated, that is 51 mm square, is less than AST minimum, that is 166 mm square. So AS minimum will govern the reinforcement at top. So considering 12 dia bars, which is the minimum to be considered. So 12 dia, so let's calculate the number of bars. So 166 upon area of 112 mm bar. So area of 112 mm bar is 113 mm square. So number of bars is 166 upon 113. We get this two numbers. So we will be providing two 12 mm bars at top throughout the beam. So AAC provided is 2 into 113, which is 226 mm square. PC represents percentage of steel in compression. Again it is 100 AS upon BD. So PC provided is 0.279. Step 5, check for shear. Shear stress is calculated as tau equal to VU upon BD. So VU is 98.63 kilonewtons. So 98.63 into 1000 upon 230 into 352. So tau V, shear stress, actual shear stress is 1.218 Newton per mm square. Design shear strength of concrete, tau C, is calculated from table 19 of the code. Tau C is calculated based on the percentage of steel provided in tension. So tau C we obtain as 0.776 Newton per mm square. Now tau V is greater than tau C, but this value is less than tau C max. So we have to provide shear reinforcement as per clause 40.4 of the code book. So VUS we are going to calculate. That's the shear which is balancing. So VU minus tau C BD. So 98,630 minus 0.776 into 230 into 352. so which is 35,805 newtons. Now from the Codal equations where we can find out the spacing of stirrups, VUS equal to 0.87 FY ASVD upon SV. So assuming 8 mm bars or 2-legged vertical stirrups are used, so V is nothing but 2 into 50. So spacing is calculated as 0.87 into 415 into 2 into 50 into 352 upon 35,805, which is 354 mm. Now we have to check for the maximum spacing of stirrups as per clause 26.5.1.5. So maximum spacing of vertical stirrups is the lesser value of 0.75 times D or 300. So 0.75 into 352, which is 264. So 264 is adopted as this value is less than 300. So we have to provide a value which is slightly less than 264. So let us provide 8 mm 2-legged vertical stirrups at 250 mm center to center. Step 6. Check for deflection. Actual span by D ratio has to be calculated. So that is 5000 upon 352, which is 14.2. The allowable span by D ratio as per clause 23.2.1 is given by 20 into modification factor in tension into modification factor in compression. So this modification factor for tension steel is obtained from figure 4 of IS 456, page number 38. So for that we have to calculate the actual stress in steel, which is governed by 0.58 into Fy into A is required upon A is provided, so which is 223.91. So referring to the figure 4 of IS 456, we get the modification factor for tension is 0.9. Now modification factor for compression is obtained from figure 5, so which is 1.08. So now the allowable span is 20 into 20 into 0.9 into 1.08, which is 19.44. So still the allowable span by D ratio is greater than actual span by D ratio. So that means like we are safe in deflection. Step 7 is the detailing. So for any beam we have to draw a longitudinal section and at least a couple of cross sections. Now in this case the longitudinal section is shown here. At the top we are providing 212 mm throughout. So there's no curtailment. At the bottom, so in the middle part we are providing 225 mm plus 120 dia bar. And at the edges 400 mm from the face of the support. So we are going for curtailment, that is 0.08 times L effective. So we are curtailing. So we are having 2 bars all through. So 225 is all through, and additionally we are having 120 at the middle. And stirrups we are having 2-legged 8 dia at the rate 250 center to center. And the stirrups is starting from 50 mm from the face of the left support to 50 mm from the face of the right support. Now let's have two cross sections. One is at the midspan section AA, the other one is at the support. The section is BB. Now section AA has 3 number of bars at the bottom. So 225. The 225 bars are the corner bars, and the middle bar is 20 mm bar. And 220 at the top all through, and stirrups 2-leg 8 dia at 250 center to center. Now the support cross section is also the similar, but we don't have this 20 mm bar because we have curtailed it. Okay.